So we'll assume that f of x is ax plus b, where a, b are constants and unknowns. Okay, so what we're trying to do here is minimize this term e, which is the error between yi, which is basically the data point, minus f of x, but f of x is axi plus bi, but it will become minus b squared. And when we minimize this, well, first of all, we need to sum this over all the data points. So I goes from 1 to n. And when we minimize this, the minimization is done over whatever parameters we're trying to fit. In this case, the parameters we're trying to fit are a and b, or we're trying to determine a and b such that this expression is reduced. Now, from calculus, we know that in order to find that constants a and b, what you need to do is essentially find the extremum values of e. And you do that by taking the derivative of e with respect to a. And we'll also take the derivative with respect to b. So when you do this, you'll get summation I equals 1 to n 2 times yi minus axi minus b. So that's the derivative of that expression squared, right? 2y minus axi minus b. But then I also need to take the derivative of this expression. So when I take that derivative with respect to a, yi is a constant, so derivative is 0. Derivative of minus axi is going to be minus xi, and then derivative of b is 0. So this whole thing has to be equal to 0 to be an extremum value. So now what I can do is I can simplify this a little bit. Summation 1 to n. I'm going to move the xi inside. So xi yi minus a xi squared minus b xi equals 0. Okay, now what I'm going to try to do is I'm trying to attempt to get a formula which basically tries to solve for a and b. So what I can do is I can move the summation inside, which will make this 1 to n xi yi minus a summation xi square I equals to 1 to n minus b times b times summation xi Okay, so let me move things around. So if I move things around, I'm just going to basically move these two expressions to the right. I get a summation xi square plus b summation xi equals summation xi yi I goes from 1 to n. So I'll store this, I'll need this later on. Okay, here remember the unknowns are, I still don't know what a and b is. We are not able to solve for a and b because there are two constants, but then there's only one equation. So we'll generate the second equation, and that is effectively done by doing dE dB equals 0. So that will be 1 to n 2 times yi minus axi minus b. And then when I take the derivative of this whole thing with respect to b, I'll end up with essentially minus 1. because derivative of yi is 0 minus ai xi is 0. That is with respect to b. And then we have derivative of b with respect to b is 1, but that's a minus, so it's that. Okay, so let's me just move this to the next page. Okay, let me pull that -2 out and then move the summation inside. So I'm going to do 2 steps in one shot to save some time. Minus a times summation xi goes from 1 to n. And when I do summation of, in this case, effectively 1, so when I sum 1, so it's going to be 1, 1, 1, n times. I end up with n. Okay, so just rewrite this so that I move the a and b on the other side. I get a summation 1 to n times xi minus, or sorry, plus p times n equals summation I equals 1 to n. Okay, so this is my second expression. Unknowns are a and b. Okay, so now that we have those two expressions, which came from applying the principles of calculus, which is basically the extremum value, what we'll do is we'll take 1, take 2, and then solve for a and b from those. So 2 equations, 2 unknowns, we can easily solve for a and b. So I will not go through the process of solving it, but it essentially involves writing an expression for the matrix 2 cross 2 matrix, which isolates a and b. So it will be something like ax equals b, and then taking the inverse of that a, which can be done analytically. There was a formula, for example, in the exam where I showed you how to do that, and you can get the answer to a. It comes out to be summation xi yi summation xi, and I'm going to drop the 1 through n, which is understood. It's going to be, the summation is from 1 through n, minus summation xi square summation yi divided by summation xi square minus n times summation xi square. Okay, so these are different. This is you first sum and then take the square, and here you take the square and then sum, so don't mix them up. And then b is xi yi, sorry, summation xi summation yi minus n summation xi yi. Oh, I think I switched this. Sorry, my bad. This is b and this is a. In my notes, I switched the values. Okay, let's stop there. Yeah, you might have seen this before. Maybe you took an experimental methods class where they use this formula to do linear regression, but now you know how that expression comes. It comes from taking the error and then taking the first derivative of the error with respect to a and b. Okay, so first of all, when you see data like this, and you're trying to fit it, you first need to plot the data, which maybe we should do first, right? Let's just plot the data, because it doesn't make sense to ask you a question, fit a linear line. What if it is not linear trend? So what we'll do is, I have this data on my computer. I saved it as a mat file. So let's see where it is. So I've saved it in a file called poly1.mat, and I'll provide this to you. So essentially, when you go to Octave and you can let's call this clear all, close all. Just save this as main.poly1.m and then run this. It does nothing, but I do this so that it just sets the directory right. And now if you want to see what the contents are, if you do pwd tells you the present working directory. If you do ls, it lists the files. So there's a in this case I put here a file called poly1.mat that basically stores all the value, and I'll show you how to do that. You just have to say save and that file name, and it saves. So I'm going to open that file. It's load poly1.mat. Okay, and then when you run this, what you see here, if you can see it in the workspace, it actually tells you what the values are. There's x and y. If you want to see what it is, I think it's a 1 cross 11. So it's a row matrix, and I want to display it as a column matrix. So I'm going to take x transpose, y transpose, and then if you run this, it prints the value. It actually clips it, so I'm going to run it again. Okay, so if you see these values, and if you see the value here, I wrote it's the same one. So 2.0 minus the same, it's the same data. Okay. Okay, so we have the data on the computer, and then I said, how do you know if it's a linear regression? Well, first you'll plot this. Let's say figure 1, plot x comma y. I always like to show it with something distinctive. So let's say x, let's say uh, blue with the symbol O, and run. Okay, so this is what the data looks like. Okay, and you can say more or less that maybe a straight line would explain the trend. Okay, so you need to do this before you do anything with linear regression, right? Okay, so this is what the data looks like. Let's proceed now that we know it looks like a line. Maybe it'll pass through this. Okay. Now you could argue that maybe a quadratic function fits this better. So given a choice between linear and quadratic, and if you see that value in putting a quadratic, then go for a quadratic. But simplicity is always welcome. So you want to keep the you want to keep the expression as simple as possible. But of course, it may be that the phenomenon you're trying to describe is better described by a quadratic or a third order. It just depends on the situation. So in this case, linear is good enough. So let's go now to the data set and see if we can fit a straight line. And then we'll put that in Octave and see what the fit will look like. So I'll say fit a straight line to the data shown on the right. Okay, so we said that what we should do is start assuming the function f of x as ax plus b. Okay, I'm going to save some time by just copying these expressions so you have them in the notes. Okay. So what we need to do here is, for a problem like this, it's just best to deal with like maybe a table where you tabulate it instead of trying to do these calculations by hand. Like, don't start trying to do summation xi, yi, take all x's, take all y, multiply them and write it in a single line. I'll show you that putting it in a table form is much better. So we have to identify what sort of table we want. We want a table which has x, y clearly. We also want, so when you wanted to find or compute summation xi, all you do is you sum all the elements in the table. So that's what I mean by creating a table. We'll need additional elements or columns to the table. We'll need xi, yi. So we'll just take the product of these two and make another column. And then we take compute xi squared. What else do we need? I think that's it. We need x because we need sum. We need y, a column for y, so we can take the sum. We need to do x squared, so we'll have a column for that. And then xi times yi, so a column for that. So just 4 columns, I think. Yeah, 4 columns. So this sometimes it's easier to do these things with Excel. If you want to do it with Excel, that's fine too. But in the exam, you'll have to do it by hand. So let's see how to do it in the exam. So let's create this table. If you already wrote down the values for xi, you can just create more columns for xi square and xi yi. And I'll write down everything from the previous page, 1.6, 1.2, minus 0.8, minus 0.4. So this is just data. And in the exam, what you want to do is, if I give you a table, just when I give you 2 columns, just create a third and fourth column and don't rewrite this. It's just not worth your time to write this in the exam. Right? Don't make a separate table, just write it over there. Okay, maybe this is a bad area to keep a space, but it's okay. Let's just proceed. So this is going to be values from the previous page. So minus 2.7664 minus 1.8747 minus 2.7127, 0.1816, 1.0231, 2.0. What a mistake. I made a mistake here. This has to be shifted down. Minus 0.8 is 2.0852, 1.3998, 3.6906, 3.0207, and then 4.9748. Okay. Yeah. Okay, the third column is actually the easier of the two, because all you have to do is take xi and then square it. So for example, square of minus 2 square is 4. Square of 1.6 is 2.56. 1.44, 0.64, 0.16, 0, and then just a mirror of that because the values are mirrored. 64, 1.44, 2.56, and 4.0. So that was easy. Now this one is going to be the harder one because you need to take essentially this 2 and multiply with this, right, to get xi, yi. So let's do that. 5.5328, 2.9995, 3.2552, 1.4137, minus 0.0726, 0, 0.8341, 1.1199, 4.4287, 4.8331, 9.9496. Okay. Okay, so let's see what we need. We need summation of xi. So we go here, we take this first column, and then just sum all the entries in xi, right? So that summation will be here. Now, good thing here is that if you see, there's -2, there's +2, -1.6 plus, so it's essentially will reduce to 0. Okay, then we go back here and see what else we need. We need summation yi. So we need sum of the second column. So that is 7.255. We also need the summation of the third column, 34.2939. And then xi, yi is the last column. That will be 30. Oh my God, this is not right. This is summation xi squared is 17.6. And this is 34. Okay, and then we also need, let's see, we also need the number of data points, right? There is a n here. So that will be just the number of points here. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So n is 11. Let me just write it here. N is 11. Number of data points. Okay. So this is the hardest part of the whole thing. It's just bookkeeping, fitting this column, filling this table. Once you have this table, now what you do is you go back to this formula here, and then you sub in the values for xi, yi. So xi, yi summation is, if you see here, is this, right? So you take that value. Then you look at the next one, that is summation xi. So that would be 0, and so on. So you just have to take that data and then sub it in the formula, and you get a and b. So let me write this down. This is just the same thing rewritten, so it's easy for you to substitute. Summation xi, summation yi was 7.255. Summation xi, yi was 34.2939, and summation xi square was 17.6, n equals 11. Let's call those equations some name. Let's call it 3 because we already used 1 and 2. So substitute in 3 will give us a equals 1.9485 and b equals 0.6595, or y equals ax plus b, so 1.9485 times x plus 0.6595. So this is the fit we were after. Kind of tedious to do by hand, but that's how it is. You have to do this at least once in the exam. And then we will now take this expression for a and b, plug it back into our Octave and see how the fit looks like. We already have the data plotted. Okay, so here's Octave. We did a hand calculation, so I'm going to say hand calculation. And I'm going to put in the value for A. A was 1.9485 and B was 0.6595. Okay. Yeah, you could write y equals a plus bx, but what I'll do is I'll actually create another function and it'll be useful a little bit later. Say function y equals poly1 with inputs of x, a, b. We would return y equals a times x plus b. And poly1, I think twice. Okay, so this is just the same expression. When I go to plot this, what I want to do essentially is I want a line with more points than just those. So I want it to go from -2 to 2. So I will create a new variable xfit. This is just for interpolation, so I can get more data and then draw a straight line. Otherwise, it'll just be a few points. So xfit I'll put linspace. I want to put the first point. So if you see here, the first point, it's clipped. So the first point is -2, I think. Yeah, first point is -2 and last point is 2. So what I'm going to do is create 100 data points from -2 to 2 so that I can just interpolate and draw a straight line over those points. So let's go here and put -2, 2, and then by default it's 100 points. So it's 100 points in xfit. Yfit would be the polynomial I created with inputs xfit, a, and b. And then what is generated, I want it to, let's do hold on, say plot xfit, yfit. Now I want a straight line, let's say with a, say, red color, straight line. If you want to make it thicker, let's put line width 2. Save. Okay, we can now run this. Okay, so the circles are the data points and the red line is the fit. And that, I think, looks kind of decent. Trends captures the trend. Okay, so this is all good. So it looks like we've succeeded in making this fit. Now I'm going to show you how to do this without using the linear regression formula, just by coding. I'm not going to use the formula which I wrote down. There is a function in Octave and even in MATLAB which you could use. It's called fminunc. Okay. Fminunc is a function which minimizes a function subject minimize a function. So what I said when we were trying to solve this optimization problem, if you saw my notes, there it is. So remember what we are doing here is we were trying to minimize E, right? Some error term we're trying to minimize, sum of errors. So it's a minimization problem. And there are tools to do minimization. So it turns out that Octave has this function called fminunc, which does minimization of the function. So this fcn would be E, and you need to supply it with the initial guess. Here we're fitting A and B, so x0 would be A and B. So let's use fminunc to do the minimization, and if everything is right, we should expect to get the same answer as the one we got using the linear regression. It does the same thing, but numerically. So this is how I would proceed. Let's say I've never used fminunc, uh, and this is how I used to do it before there was ChatGPT. I would just go and find out a simple code to uh, use fminunc. You can pick anything. I would see if this seems like just picked up from MATLAB documentation. Uh, so minimize the function 3x squared plus 2x, 1x2, x2 square. This is how you write the function. This is how you, okay, so let's just use this. It's something from the internet. Okay, let's go here. Okay. And remember, this is actually in two variables. There's x1 and x2. And this is exactly what we want. We want a and b, right? So let's save this. Should be saved as my fun. And then there is the driver, which is calling this function, which is this one. Let's go. Then let's go to main poly. And then I'm going to just, I think that can stay. So that's hand calculation. Let's do fminunc. Okay, so this is solving a very different problem, which is not even connected to it. But I want to first get fminunc to work and understand it perhaps. So I run this. Invalid function handle, unable to find function for my fun. Okay, there is x0, my fun. Don't see a problem. Uh, find a function. Okay, sometimes this is a thing, this is a, sometimes Octave does this funny thing, at least on Windows. I'm going to restart Octave and see if it goes away by restarting it. I've never had this problem on Mac. Okay, let's see if it works now. Otherwise, there's something wrong with my function. Okay, so it was actually an Octave problem. So here it solved the problem. The solution is 1e negative 9, 1e, that's pretty much 0, right? It's almost 0. And the function value is 0. And that makes sense. If you go here and look at this function, it's a function which has square terms. That could, yeah, that could actually be negative, but it can never attain a negative value, apparently. It can only be positive. I think you can rewrite this as sum of two square terms. And if it's a sum of two square terms, something like that can never be less than 0. Um, I mean, if you want to see it, you could write it as x1 plus x2 square. So I'll give you x1 square plus x2 square plus 2x1 x2 plus 2 times x1 square. So you see this is the same as that one. So it says you have sum of two squares. And when it's a sum of two squares, you can never have a negative value. The minimum value for a sum of squares is always 0. And so it chooses x1, x2 to be 0. Okay, so that's the reasoning. Now, we don't really need to know all that for this one. I just wanted to get to work because now I'm going to modify it. So I have this working now. All I need to do now is modify it with what I need it to do. I need it to essentially minimize this expression. So I need to pass this as inputs to the function my fun, and then we'll go from there. So this has to take in more arguments. Let's see, it has to take x0, so it has to take in x. Let me also send it. Oh, now there's going to be a problem here. I think there's going to be a problem because I have x here and then there's another x. So let's just call this constant c, c, c. Let me just check if it works. Never make too many modifications because then you don't know if it will work or not. Oh, I'm doing a time. Okay, 10 minutes is enough. It worked fine. Now I'm going to make this change because, okay, and then, okay, it worked fine. So C was fine. Let's change this now. Now I want it to, like, I want this function to take X. Well, I'll change that X to C. So I don't want to confuse with X. I also want it to have X and Y. What is X and Y? That's my data. And I want to change this return argument to this error. And what does that look like? Well, it looks like E equals sum y minus ax minus b. So this is what I'm trying to reproduce. So for that, all I need to do is say E equals let's say A is, let's say it's stored in 0, sorry, first element. B is stored in the second element. And so then I can do y minus 8 times x minus b. So when you do this, y is a column vector, x is a column vector. So it's going to give you, E will be a column vector. So what you want to do in this case is take the square. So that would be taking the square of two columns and then multiplying them together. And once you multiply, then you do the sum. Okay, so this is what I want it to do. Can be done in one line. If you want to break it down, which you should if you think was hard, I could actually visualize what's going on every step, but if you could do something like this, you could say error equals 0. Then I would run a for loop, 1 to length of x. For each element, I'm going to populate the sum. E equals E plus y I minus a times x I minus b squared. So this takes the first element, computes that error, squares it, adds it to E, and keeps doing that for all the 11 columns, 11 elements, and then returns that. Okay, it's always a good idea to check if this works. Let's go here and comment this out. Yeah, let me check if it works for this. So let's see, the input is C0 and E, and then let's run this. Okay, so okay, it printed 22.032. There's an error here. Not error, but I should suppress this and go here and then, okay. So it's actually, why is it printing something? Oh, I did this. So let's move that and run. Still printing this. I don't want it to print all this. Why is it printing it? This suppressed. That's suppressed. Oh, because of this. I see. Okay. Now run this. Still printing. Did I suppress? No, it's not here. We do CLC. There is something in here which it is. So that's not printing. It's not printing. Shouldn't printing. Okay, let's see this. I have no idea why it's printing this. 100 looks like. Okay, it doesn't affect any results, but that's just bothering me that it's printing this when I've suppressed all prints. Maybe it's in polyfit. Maybe there. Yeah, here it is. Yeah, that is. Okay. Okay, now it shouldn't print. So I could make it print the error. Okay, 22.03. Okay, I got 22.032, but clearly that is not the minimum. I need to find the minimum. I have to use fminunc. So that's working. Let's suppress that. Let's play with this. I want to do this optimization. Okay, now there is a slight syntax thing which you should know, which is if you're trying to pass an argument like this, where there is C, X, and Y, there's something which you need to know, or you need to figure it out by looking at documentation. The way this is passed should be C, comma A, comma B, and then I should put this handle like this. Okay, so this ensures that I pass additional arguments A and B to my fun. So let's run this. So it gave me 0.70161 0.522. That's for A and B. Okay, this is what I got. A equals 1.9485.6595. This is not the same as this. There's some problem. Okay, I need to figure the bug. Okay. See, A and B. The first argument is A second, AX plus B, okay? Okay, if you find it, let me know and I'll fix it. And the error seems too small. In fact, if you get something like this, you could actually check this. We could make it fit this. So we have just like this. Poly 1 X fit AB. Instead of AB, we'll put C1, C2, and then it's the same thing, and then see what it gives. Syntax error. Okay, sorry. Yeah, this doesn't work. So what's the error? Well, turns out, I think I did a mistake here. The inputs to my phone is X and Y. I don't know why I put A and B here. It should be X and Y. Let's see if this works. Okay, that's the fit. If you look at the constants here, which I obtained, I got for C 1.9485. So if you go here, by hand calculator, I got 1.9485, and B was 0.6595 points, exactly the same thing. So this is a way to do this without using linear regression, just also works. So if you want to put both of them now together, what I would do is I'll get yfit. I'll call this yfit2, and then I'll yfit. Well, let's just put it on a different plot. So subplot, I'm almost done. 2, 1, 1. Okay, so that does one plot. And then here's the other one, XY, X fit is the same, Y fit is Y fit 2. Let's give it a different color, say black. So, okay. And then I should put this on a different plot. So sub plot 2, 1, 2. Okay, run this. So those are the two answers. They look exactly the same, no wonder, because the constant was same. So here's a very powerful way of doing a fit. Now, turns out that this is very general. This fminunc, you could change that polynomial to anything else. There's something which I should have done here, which is to make it generalizable, which I missed. I should not write it like this. I should actually write it exactly like this polynomial. So I should put, let's go here, and then fix this my fun E equals E plus yi minus poly xi. So that way, it's only one place you need to modify that poly one. So if you do this now, hopefully it will still work. Yeah, it still worked. This is the function value. So now the thing is, if you want to change this from linear to quadratic, that's the only thing you need to change. It'll still work. This code is very general.